Okay, this is 2.8, video 2. So in the first video, we talked about the concept of related rates and how everything that is changing with respect to time. And we did a few examples of those. This one's going to be a slightly more involved example. And there are multiple ways you could go about doing this. I'm just going to show you in my case one way. So it says a water tank has the shape of an inverted right circular cone of altitude 12 feet and a base radius 6 feet. So there's a lot of vocabulary right there in that part alone. So let's walk through that one. It says, first of all, the water tank has the shape of an inverted right circular cone. Inverted meaning upside down, right circular cone. So believe it or not, you can have cones which don't have circular bases. They can have elliptical bases, and they don't have to be right cones. You can have oblique cones, which means that they're kind of slanted. Really kind of weird to see, but you can have those. This one basically just looks like your standard ice cream cone or something like that. So that's what we're going to sketch over here. It's going to be something that looks kind of like an ice cream cone. So we've got our top, and then we've got the cone part, something like that. Again, you don't have to be a complete artist, but at least get the general idea. And it says that the altitude, which is just a fancy name for the height, the altitude is measured from the vertex of the cone, so from the vertex of the cone, perpendicular to the base. And the base here is on the top because of the fact that it's inverted. And it also says it has a base radius of 12. Well, the base radius goes from the center of that circle out to the edge. So we know that the altitude of this thing is 12. That was the height. The base radius is 6. Okay, so they've given that to us. That's at least a good start. If water is being pumped into the tank, so we've got water being pumped into the tank at a rate of 10 gallons per minute, approximate the rate at which the water level is rising when the water is 3 feet deep. And it tells us that 1 gallon is approximately 0.1335 feet cubed. Okay, got a lot to decipher here. First of all, some given information. We do know that water is being pumped into the tank at a rate of 10 gallons per minute. Okay, now just looking at 10 gallons per minute, it might not ring a bell as to what that is specifically. But when it says that a gallon is 0.1335 feet cubed, because of the fact that it's cubed, should tell you that that is going to be a change of volume. So the water is going to be pumped in, and it's going to be changing the volume. So we're going to write this as dV over dt is 10 gallons per minute. But it does say that 1 gallon is 0.1335 feet cubed, so we can actually write that. Well, if 1 gallon is 0.1335, multiplying that by 10 gallons is going to be 1.335. So this is the same as 1.335 feet cubed per minute. And the reason it's important to change that is because everything else here is in feet, so the units do need to match. It says we want to find the rate at which the water level is rising. So I'm trying to figure out how much the height is changing. So I'm looking for dH over dt. Specifically, it says when the water level is 3 feet deep, meaning that the height of this thing is 3 feet. So I already used blue, but we'll just say that like down here is our 3 foot level. So we want to do this specifically when h is 3 feet. All right. The problem is now we have to come up with an equation that relates both the volume and the height. Well, I do know that the volume of a cone, we can write that one out, is 1/3 pi r squared h. And if you've never really thought about this before, one way to think about this, because a lot of people are like, I don't ever remember the volume of a cone. So the way I think of it is you've got pi r squared in there. Pi r squared is just the circle. That's the bottom. But then you've got this h part. Well, that would be the height. And if you really think about it, if you took a disk, which is pi r squared, or a circle, pi r squared, and you stacked a whole bunch of those disks up on top of each other, really what you're going to get is a cylinder out of it. So I'm going to erase this part in a second, but really what you would get is a cylinder that would look something like that. But then if you were to take off the outside 2/3, so you chop off all of this stuff right there, then you're left with 1/3 of that cylinder. So again, think of it, pi r squared, that's the disk. You got pi r squared h, that's a cylinder because you're stacking a whole bunch of disks up, so you've got a disk times a height. And then if you chop off the outside 2/3 of it, you get a cone, which is 1/3 of it. So I'm going to go ahead and erase all that stuff that I just put there in red, just because it's not really necessary for this problem. Love the back button. It's awesome. Okay, so now I have an equation that has volume, in this case radius and height, and they're all changing. Think about it. If the water level is going up in the cone, if you're filling this cone up, the water level is rising. So that means the radius is changing, because as the water level gets higher, the radius is going to change. The height is obviously changing because the water level is rising, and the volume of stuff that you're putting in there is changing. All three things are changing over time. The problem is I have no information here about how the radius is changing. As a matter of fact, it didn't tell me anything about the radius at all, other than the base radius of the actual cone itself was 6. So what I need to do is I need to kind of look at this. I'm going to split this off to the side here. I need to look at this piece right here that I drew in green. You look at that carefully. It forms a right triangle. And one thing we know about this is that if this part right here is at your 3 feet level, so let's just say that that's the right triangle right there, that's the top of it at the 3 foot level. One thing we know about that is that it's going to be a similar right triangle. As a matter of fact, I'll kind of sketch it in orange here. This piece right here is what I just split off. So let me trace that over, I guess, in orange. I don't know what green and orange makes, but that's what we're getting here. All right, so what I do know is that I do know that if they are similar right triangles, they're proportional to each other. So the orange triangle is proportional to the big green triangle. Okay, that's one of the properties of similar triangles. So what I know is that this represents the height, this represents the radius. So if they are similar, if they're proportional, it means the ratios of each piece is going to be equal to the other one. So I know that 6 over 12, because that's the radius of the large green triangle over the height of the green triangle, 6 over 12 is going to be proportional to or equal to the radius of the little triangle over the height of the little triangle. Okay, that's properties of similar right triangles, taking us all the way back to geometry concepts. Well, I can go ahead and cross multiply here, so we'll get 12r equals 6h. What I'm trying to do, by the way, by doing this, I'm trying to get rid of the r, because I don't have any information with r in my original volume equation. So I want to solve this for r. Well, to solve this equation for r, I'm going to divide both sides by 12. 6 over 12 is a half, so I get 1/2 h. The nice thing is, because now I've solved this for r, I can take 1/2 h and I can substitute it in for that r. What that's going to leave me with up here is an equation that only has volume and height left in it, which is good because I'm looking for how the height's changing. I know how the volume is changing, so that should be everything that I need. So my volume equation is now going to be 1/3 pi. I'm going to replace the r with 1/2 h. Don't forget it's getting squared times h. Let's simplify. I want to do all the simplification that I possibly can before I start taking derivatives. So the volume is going to be 1/3 pi. 1/2 h squared is 1/2 h times 1/2 h, so that's 1/4 h squared times h. And then that's going to be 1/3 pi 1/4 h cubed. Now, yes, I certainly could have multiplied the 1/3 and the 1/4 together. I didn't do that for a specific reason because I already know what's coming. Now I'm able to take a derivative, and it makes it pretty nice. If I take the derivative of v, It's going to be changing over time, so that's dv over dt. I can bring the 3 from the h out and multiply it by the 1/3, making 1, so that goes away. So we got pi times 1/4 h squared now. And don't forget, h is changing over time, so it's times dh dt using the chain rule. Now I should have everything that I need. I'm solving for dh over dt. They gave me dv over dt. So I can plug that in. That's 1.335 for dv over dt equals pi times 1/4. The height was 3. I remember that one. dh over dt. So now to solve this thing, the good thing here is I believe up in the problem it says approximate, which means that we are going to end up using the calculator because we're going to get some messy decimals here. We don't have to leave this thing in terms of pi. However, to go ahead and write it out, I'm going to divide everything by basically pi times 1/4 times 9 in this case, or 9/4. So I'm going to get 1.335 divided by 9/4 pi. And that's going to be my dh over dt. Make sure you plug this stuff into your calculator the correct way, because if you don't, you're going to end up getting the wrong thing. I would strongly suggest putting the 9/4 pi in a big parentheses when you divide it, because otherwise you may end up multiplying by something you don't intend to. So dh over dt, after you put that into your calculator, and I already did that, is 0.188 feet per minute. Now, how do I know that it's feet per minute? Well, height is the thing that's changing. Height is linear. It's one-dimensional. Okay, it only moves in one way. So in this case, it's going to be feet, not feet squared, not feet cubed, feet per minute. And then you would go ahead and write your sentence. I am not going to keep writing the sentences just to save a little bit of time, because I want to move on and get at least one more example on this video. But that's it. 0.188 feet per minute is positive, which means that it is increasing. So the height is increasing. Makes sense. Make sure that your answer makes sense to the problem. Okay. The setup of this one is pretty interesting. And again, there's multiple ways you could go about doing this. I'm just going to show you the way that I think to do it. So a light is on top of a 12-foot vertical pole. A 6-foot woman walks away from the pole base at 4 feet per second. How fast is the angle made by the woman's head, the light, and the pole base changing 2 seconds after she starts walking? Okay, so let's go ahead and sketch this one, because this is not easy to see. We have a light on top of a 12-foot vertical pole. So here's our light shining brightly. 12-foot vertical pole. A 6-foot woman, so that's going to be about half the, there's my 6-foot woman walking away from the pole base. So she's walking in that direction. Okay, so let's see, what are we given? The 12-foot pole, I've already done that. The woman herself is 6 feet tall. She's walking away from the pole base, so I actually probably should have put the arrow over here, because she's walking away from the pole base at 4 feet per second. Well, since that's a horizontal, we'll call that a dx dt. And that would be 4 feet per second. How fast is the angle made by the woman's head, the light, and the pole base changing 2 seconds after she starts walking? Well, the one thing I do know out of that is that t is 2. Given is going to be a dx over dt. That's 4 feet per second. We are trying to find out how fast the angle is changing. Well, we're going to measure an angle, probably using theta. So we're going to say that it's d theta over dt is what we're looking at. Now the question is, where specifically is the angle? If you remember how you actually label an angle, the angle part of it, or where the angle is going to be, is by the middle part. So it says from the woman's head to the light to the pole base. So from the woman's head to the light to the pole base. So here is your angle. That's what we're looking for. How fast is that angle changing? Okay, obviously this thing is going to cast a light down here. That can be important for other problems. So we'll just go ahead and extend this triangle out. We aren't actually going to need that specific triangle in this case, but could be important for other types of problems. So we want to know how fast that angle is changing. Well, let's see. We can figure out a couple of things here. We can figure out that this right here is a similar triangle to the big triangle. We don't even need the big triangle here, however. I know that the woman is 6 feet tall. The pole is 12 feet, which makes this side over here 6. That's of this small triangle right here. I know that the distance, well, I can figure out the distance. If she walked away from the pole at 4 feet per second and she walked for 2 seconds, she traveled 8 feet. So that's 8. And then again, by using Pythagorean theorem, if we need to, I don't know if we do, but if we need to, we can find the hypotenuse, which in this case is going to be 10. Okay, and that's using Pythagorean theorem. Again, not writing that part down. But the important thing is here, I'm looking for how the angle is changing. When it tells me I'm looking for something with an angle, I should automatically be thinking trig. Okay, we know something about how the x value is changing. We know something about the height of the pole. Fortunately, the height of the pole is not changing. Don't really know too much about how the hypotenuse of that triangle is changing, because it will be changing as she walks further and further away. But we don't have any information on that. So I'm thinking that we should probably be using tangent, because I know something about the opposite, which is the 8, and the adjacent, which is 6. So we're going to use the tangent of theta is going to be the opposite, which is an x value, over the adjacent, which in this case, now this is something we can plug in right away, because we know that the height between her head and the top of that pole is not changing. If she's walking horizontally, it's always going to be 6. So that can actually be plugged in right away. If you weren't sure, you could have just put a y there for right now, but you realize y is not changing, and you can plug in the 6. All right, so to make it a little bit easier, I'm going to go ahead and multiply both sides by 6. So we're going to get 6 tangent of theta equals x. Now we can take a derivative, because that relates everything. So the derivative of 6 tangent of theta is going to be 6 secant squared theta. Don't forget theta is changing, so chain rule says d theta over dt, which we kind of need because that's what we're solving for. And then the right side is the derivative of x is 1 dx dt. And now we can see if we've got the things that we need. Well, I have d theta over dt. I'm sorry, I don't have it. I've got it in my equation, but that's what we're solving for. I have dx dt. I don't have theta, however. Okay, we don't actually know what theta is. We could go through a whole bunch of trig to solve for it, but it's not really necessary, and I'll show you why in just a second here. So the first thing we're going to do is we're going to go ahead and plug in the 4 for dx dt. Still solving for d theta over dt. And I don't yet know theta. But I'm going to solve this now for d theta dt just in general without knowing theta yet. So I'm going to divide by 6, which 4 over 6 is going to reduce to 2/3. Now I'm going to divide by secant squared. If I divide by secant squared, it's going to put the secant squared in the denominator. But the reciprocal of secant squared is the same thing as cosine squared. So dividing by secant squared is the same thing as multiplying both sides by cosine squared. This is where knowing some of those properties really helps. So dividing both sides by secant squared is the same thing as multiplying by its reciprocal, which is cosine squared of theta. Okay, so now I've got everything in place. The only thing I have to do is figure out, how do I figure out theta? Or do I need to figure out theta? I don't need to figure out theta, because I do know that cosine is the adjacent over the hypotenuse. So I guess I actually did need the hypotenuse here, because the adjacent is 6, the hypotenuse is 10. So cosine of theta is 6/10. But then I'm going to have to square it because it's cosine squared. So what ultimately we're going to get here is that d theta, whoops, didn't mean to erase, d theta over dt is 2/3 of 6/10, which reduces to 3/5 squared. Okay, and then go ahead and simplify that. So 3/5 squared is 9/25. So that's going to be, let's see, it's going to be a 9/3. So that's going to reduce to 3. So it's going to be 6/25, I believe, is what we get there. If I did that right in my head, hopefully I did. Now the question is, what are the units? 6/25 what? Well, there's only two ways you can measure degrees. Degrees are going to be measured in radians, or I'm sorry, not degrees, angles. Degrees or radians is what we're looking for. Because this didn't say anything about degrees or have a degree symbol, we assume that it's done in radians. So this is going to be radians per second. Radians per second. So the angle is changing at a rate of 6/25 radians per second at the moment in time of 2 seconds. Okay, that's at least the way I thought to do the problem. There are other ways to do it, but that's the way I thought to do it. Okay, again, like I said, this is a very large section, so we've got several more examples. I'm going to stop this video. I will probably try and move through some of the other ones just a little bit quicker. There might actually be 4 videos in this lesson.